Okay, this is Matter and Measurement, Lesson 6, and this is actually going to be the last lesson in the first unit that we're doing. So that means two things. One, you need to start studying the vocabulary terms that I put a link in Schoology for Quizlet for, because we will have a vocabulary quiz, and you need to start reviewing everything for a unit exam. On Monday, I will give you a practice test that you can start working on. Okay, so let's finish this up. In our last lesson, we were talking about how we determine the number of significant figures in a value. And we used the Atlantic and Pacific rule, and we also used just standard rules. Today we are going to learn how to handle calculations involving significant figures, specifically adding and subtracting, multiplying, dividing, and we are going to talk about how we measure matter and calculate error. So, rules for sig figs and calculations. The general rule is the final answer must be expressed in the lowest amount of significant figures that were originally given to you. You can't create accuracy when you didn't have it to start with. In multiplication and division, you're going to first and foremost just do the math. Then you're going to express the answer in the least number of significant figures using the values that you used in the computation. So for example, over here, 12.257 has 5 significant figures. Decimal present is the Pacific rule. We start on the left, the first non-zero digit, count it, and everything after it. So this is 5 sig figs. It's a sad looking 5. Okay. And 1.162 is 4 sig figs. So that means that our answer will have 4 sig figs. Express the answer in the least number of sig figs. So when we do the math, 12.257 times 1.162, we're going to get 14.242634. Now, we certainly don't want to write this for an answer, but 4 significant figures would be 1, 2, 3, 4. It would end right here with the 4. What I need to remember to do is look to the right, see if this value is 5 or greater. If it is, then we would round this up. 2 is less than 5, so where there's no rounding that happens here. So my answer is 14.24. And that's my final answer. So that's multiplication and division. Do the math and express the answer in the least number of sig figs. In addition and subtraction, you're going to line up the decimal points and you're going to round your final answer to the lowest decimal place. So if you're adding two numbers and one goes to the 10th place, 1 place beyond the decimal, and one goes to the 100th place, 2 places beyond the decimal, then your answer would only have 1 decimal place. So when we look at these three values that we're adding, 3.95 has 2 decimal places, 2.879 has 3, and 213.6 has 1. So what that means is that our answer can only be to the 10th place. But just like in multiplication and division, you're going to do the math first. So when we add these values, we get 220.449. So to the 10th place, we look to the right, it's less than 5, no rounding, so our answer is going to be 220.4. So let's do 2 examples here. 5.14576 minus 2.31. I get 2.8356. So I get 2.8356. However, it's subtraction. And this has got 4 decimal places, this has 2, so my answer can only be to the 200th place. I look to the right, this is a 5, so that means my final answer is going to be 2.84. Okay, on the next one, we're dividing 69.25 divided by 45.8, and we get a really long number. I'm not going to write the whole thing, but we get 1.512 0.200, and there's some other values. So this has got 4 sig figs, 6925. This has 3. Our answer can only have 3 sig figs, which means it's going to be to the 1. Look to the right. There's nothing to round here, so 1.51 is my answer. Okay, let's look at rules for calculations with numbers and scientific notation. When we're adding or subtracting, all the values must have the same exponent. The result is the sum or difference of the mantisses. And we multiplied by the same exponent of 10. So basically, you're not going to be doing hand math, but you can see this is 10 to the 6th and this is 10 to the 5th. They're saying that they should have the same exponent. And then you would subtract them. So what you could do in this case, if you were having to do the math by hand, you could change 2.3 times 10 to the 5th and get the right exponent. So I'm going to show you both ways, all right? So to get these to equal, I could make this 0.23 times 10 to the 6th. Okay? So 2.3 times 10 to the 5 and 0.23 times 10 to the 6 are exactly the same values if we were to write them out in standard form. So now my exponents are the same. So now all I have to do is subtract the mantisses, 4.5 minus 0.23, and I'm going to get 4.27. Okay? Now, when we look at our original values and determine how many sig figs, we're leaving the exponent part out of it. So we're only evaluating 4.5, okay, and 2.3. And this is addition and subtraction, so our answer can only be to the 10th place. So here. So I'm going to look to the right, I'm going to round this, so this becomes 4.3, and my exponent is now 10 to the 6th. So 4.3 times 10 to the 6th. You're going to be using calculators. You would never have to do this by hand. So in your calculator, you would put this whole thing in parentheses. You'd put 4.5 times 10 to the 6th minus 2.3 times 10 to the 5th in parentheses, and you'd get the same answer. In multiplication, the mantisses are multiplied and exponents of 10 are added. So in this one, if we multiply these two values, and I'm just going to do it in my calculator because it certainly makes it a whole lot easier. I'm going to put parentheses 3.1 times 10 to the 3rd, and I'm going to multiply that by 5.01, and that's in parentheses, times 10 to the 4th. And I get an answer of 1.55, and that's going to be times 10 to the 8th. Now, before I write times 10 to the 8th, we need to look. We're multiplying. This has 2 sig figs. This has 3 sig figs. When we multiply or divide, our answer has to be to the least number of sig figs. So that would be 2 sig figs. That would be to the 5. I look to the right. I have to round this. So it's going to be 1.6 times 10 to the 8th. And in division, the mantisses are divided. That's these values out in front. And the exponents are subtracted. But we're going to do this right in our calculator. And you should try to do it in your calculator to make sure you get the same answer. If you're not getting the same answer, then it's a calculator issue. You're not doing something right. You need to come see me so we can straighten this out before a test or a quiz. So we've got 7.63 times 10 to the 3rd, and we're going to divide by 8.60, 6. Try that again. divided by 7.63 times 10 to the third divided by 8.6203 times 10 to the fourth. And we get, I'm going to write it this way first. Your calculator will probably give it to you as 0.0885, a bunch of other numbers. So let's see what we have here. We have 3 sig figs here, and we have 5 sig figs here. Our answer can only have 3 sig figs. So if we put this in scientific notation, we're going to get 8.85, and that's 2 times 10 to the negative 2. So we have 3 sig figs, and it's in scientific notation. That's our answer. Okay, moving on. Finish up with something easy. Measuring matter. What's the difference between mass versus weight? Well, hopefully you learned this in 8th grade physical science. Okay, let's change color here. So we know that mass is how much matter something has. How much matter. And we know that weight depends on gravity. So the force of gravity pulling something to the earth, or, another planet, depending on where we are. So what do they have in common? Well, what they have in common is that they are directly proportional to one another. So as mass increases, I put an up arrow. You can write the word increases or put an up arrow, whatever's easier for you. Weight increases. And that should make sense, because the more mass you have, the more that gravity will affect you, because weight not only depends on gravity, but a component of that is mass. In chemistry class, we really only work with mass. We have the same mass whether we are on Earth or we're on the moon. The different forces of gravity on each cause us to weigh more on Earth than on the moon, though. And that's why we float on the moon. Volume is the amount of space that an object takes up. And there's 3 ways that this can be calculated. For liquids, we use a graduated cylinder. You used one of those in our first lab. For a regular solid, meaning a square, we're going to do length times width times height. So here our volume will be measured in milliliters. Here, length times width times height will more than unlikely be centimeters cubed, our final unit, cm times cm times cm. And for irregular solids, we are going to use the water displacement method, which I know that you all used in earth science. And actually talking about density is going to be a nice segue for us, because we're actually going to do a density lab this week. I know that you've done one in earth science, but because density is mentioned in this first unit, we do a pretty simple density lab, and should be straightforward, no problems. You guys will just breeze right through that. So density is the amount of mass in a given space. It is the ratio of mass to volume. The formula is found in Table T of your reference tables, so we're going to start using our reference tables. Table T is the back page if you flip the reference tables over, and you will see density equals mass divided by volume. So in this box right here, we have box A and box B. Which box has a higher density, and explain your answer. I know that all of you chose box A for the higher density, and I know that you're all saying because there are more particles or more balls in the same amount of space. So there's more per unit volume. All right, we're going to finish up with some basic density problems, and then we're going to talk briefly about error, which I know you also calculated in Earth Science. That'll be it, and that's the end of Unit 1. One thing that you may not know or may not remember is that the density of water is 1 gram per milliliter. And this is if we're talking about displacement method. If we're talking about density, the units in displacement is grams per milliliter. If we are talking about, or that actually, yeah, or they could be 1 gram per centimeter cubed if we're talking about a regular object. So you may have used these units in Earth Science. What most of you probably don't know, and is pretty important, okay, for water, 1 milliliter is equal to 1 centimeter cubed. So this could become very useful as a conversion factor. Just like 12 inches in a foot, well, we now can add 1 milliliter equals 1 centimeter cubed to our repertoire. What is the density of an object with a mass of 60 grams and a volume of 2 centimeters cubed? So density equals mass divided by volume. We always write our formula. Then we substitute in. So density equals 60 grams divided by 2 cm cubed. And our answer is going to be 30 grams per cm cubed. All answers must have a formula, substitution, and answer with units. Okay? 60, no decimal, has 1 sig fig. 2 has 1 sig fig. Our answer has 1 sig fig. If you had a gold brick that is 2 centimeters by 3 centimeters by 4 centimeters and has a mass of 48 grams, what is its density? So density equals mass divided by volume. However, we know that volume of a regular object is length times width times height. So that's going to give us 2 cm times 3 cm times 4 cm. So 2 times 3 is 6, times 4 is 24 cm cubed. So now we can do that over here. Density equals 48 grams divided by 24 cm cubed. And we get an answer of 2 grams per cm cubed. These should be pretty straightforward and easy. This is just a review. You had the summer off. If a block of wood has a density of 0.6 grams per centimeter cubed and a mass of 120 grams, what is its volume? So density equals mass divided by volume. And what we do then is we're not solving for density. We're not solving for density, we're solving for volume. Now there's 2 ways we can do this problem. I know your math teachers probably tell you to do this, okay? So you're going to have 0.6 grams per cm cube over 1 equals 120 grams over x. And you can cross multiply and divide. So you've got 0.6x equals 120. You get 200. So this is going to be, and your grams cancel. So you get 200 cm cubed. Now, I want to show you another way because there are some formulas that you're not going to be able to set up as a proportion. And you need to be able to manipulate a variable, any variable, in an equation to solve for an unknown. So, going with our original equation, d equals m divided by v. If I want to solve for volume, that means I have to get v by itself and it has to be in the numerator. So all you do is reverse order of operations. Here, mass is divided by volume, so we're going to multiply both sides by volume. These cancel. But I still don't have v by itself. So to get v by itself, these two are multiplied. I'm going to divide both sides by d. d divided by d cancels. So what I'm left with is v equals m divided by d, which in what we were doing was the exact same thing, 200 divided by 0.6, not 200, 120. 120 divided by 0.6 equals 200 cm cubed. So you can get away with it doing this way for right now, but later on when we get into more complex formulas, you're going to have to be able to manipulate an equation to solve for an unknown. Two more. What is the mass of an object that has a volume of 34 centimeters cubed and a density of 6 grams per centimeter? Well, you can set up your proportion if you want, but I'm going to show you the way that we need to solve this. If I am solving for mass, I need mass by itself. This is divided. I'm going to times both sides by v. These cancel. So m equals v times d. So that means mass equals 34 cm cubed times 6 grams per cm cubed. My cm cubes cancel. 34 times 6 gives me 204, and my grams are my unit. Last problem. Which is heavier, a ton of feathers or a ton of bowling balls? Which is heavier? Hopefully, I did not trick you. Both are the same. Because they weigh 1 ton. Okay. And last, let's just quickly review error. Percent error, I'm sure that you did this in earth science. It's the measurement of the percent that the measured value is off from the accepted value. The measured value is the value you get, and that's experimentally. Sometimes the measured value is called the experimental value. The accepted value is the value you should get. This formula is also found on the back in Table T, exactly in the same spot as the density formula. So percent error is equal to the measured value minus the accepted value divided by the accepted value times 100. Now, what I tell students, and it's really up to you, is, and they don't write this on the back of your reference tables, you have to remember that percent error is always a positive value. Well, in some cases, if your measured value turns out to be less than your accepted value, you would get a negative percent, which is impossible. So you kind of have to remember that the numerator is absolute value. And I don't know why they don't put that on the formula, but they don't. So if you ever compute something and you get a negative percent, just get rid of the negative. It should be positive because the numerator is always absolute value. So if negative, it means that your measured value is less than the accepted value, but we don't report it as negative. If it's positive, your measured value is greater than the accepted value. Let's just try one to finish up. In a lab experiment, you are told by your teacher that the actual value of can of Coke is, sugar in a can of Coke is 39 grams. You experimentally determine it to be 30 grams based on your own data and calculations. What is your percent error? So percent E equals measured minus accepted over accepted times 100. So percent E equals 40 minus 39 over 39 times 100. Now, 39 grams has 2 sig figs, 40 only has 1 because there's no decimal. So when we do the math on this, 2.56% error, and since we can only report it to 1 sig fig, we're going to have to make this 3% error. Okay, that's it for Unit 1.